Hello everyone, I'm Bounty. I'm going to talk about our work, fast, flexible, and comprehensive bug detection for persistent memory programs. This work is in collaboration between the Hunan University and the University of California, Merced. Developing PM programs with crash consistency is challenging. Some bugs are caused by the missing data durability or violating the ordering constraints. For example, if the program missing the read back or fancy instructions, the updating becomes volatile. For ordering constraints, if the program misses fancy instructions, X and Y may be reordered. Meanwhile, various persistent models have the different constraints for data durability and ordering constraints that make the developing crash-consistent programs more complex. To solve it, we require PM-specific debugging tools to help us. In this work, we first characterize PM programs in terms of how store, write back, and fancy instructions happen and getting through the PM program patterns. Then, depending on these patterns, we design PM debugger, which use the PM-aware data structure to achieve faster bookkeeping of memory locations and persistence. In addition, PM debugger defines 9 checking rules and supports 2 relaxed persistent models, so it supplies more bug coverage. As a result, PM debugger requires less user annotations and less debugging time. PM debugger found 19 new bugs in memory cache and 2 new bugs in PMDK. All bugs are reported to developers confirm them. Next, I introduce our PM characterization study. We first studied characterization of a fancy instruction in PM programs. We found the durability of 77.7% of stores is guaranteed by the nearest phase, and the durability of 4.6% of stores is guaranteed by the second phase. Based on the above observations, we identified the first PM program pattern. For most stores, the data durability is guaranteed by the nearest phase. We can get inspiration from this pattern. Tree reorganization in the traditional bookkeeping has a few opportunities to gain performance benefits, because the information of most stores is deleted in the short term. Then we study characterization of the store instruction in PM programs. We first split stored instruction into the intervals by write-back instruction and store instruction between the two neighbor write-back instructions form a write-back interval. If a single write-back persists all stores in the write-back interval, we call it as a collective write-back. If a single write-back only persists partial stores in the write-back interval, we call it as a dispersed write-back. As a result, more than 71% of the all write-back intervals has been collectively flushed. Based on the above observations, we identified the second PM program pattern. Stores in the write-back intervals are highly likely to be flushed together by the same single write-back. We can get inspiration from this pattern. It's promising to collectively maintain and update the persistent states of the memory location for high performance. Last, we count the number of store write-back and fancy instructions and found, in most of the benchmarks, store accounts for 70% of the 3 instructions. In all benchmarks, store accounts for at least 14.2%. Based on the above observations, we identified the third PM program pattern. Store happens more frequently than the write-back and fancy instruction, so we must efficiently process store instructions. Next, we will introduce our debugging tool, PM debugger. PM debugger directly debugs the bind file of PM programs and instruments memory store, write-back, and fancy instructions. PM debugger splits the instruction trace into intervals by fancy instructions. We call it as a fancy interval. Within a fancy interval, there is at least one write-back interval. For data structure, PM debugger uses a PM-aware data structure for a bookkeeping, including a memory location array and a AVL tree. A memory location array consists of metadata and memory location information. Memory location information records the information of a store. Metadata records the information of a write-back interval. The AVL tree is used to receive memory location information from the array. Using the array structure, memory location information can be directly inserted into the array structure without reorganization. Such faster processing of store is necessary due to pattern 3. Using the metadata, PM debugger enables faster query and collectively updates memory location information when the processing write-back instruction. Pattern 2 suggests this design. When processing the fancy instructions, PM debugger can simply invalidate the metadata to enable much faster memory location information deletion. and redistribute some memory location information from the array to the AVL tree to gain the long-term benefits of the quick searching. This design is driven by the Python 1. Meanwhile, PM debugger automatically verifies the information to check bugs according to the defined checking rules. Now we show evaluation results. For performance, compared with PMI check, PM debugger achieved 2.5 times the performance improvement on average. Compared with the XML detector, PM debugger achieved 49.3 times performance improvement on average. Compared with PM test, PM debugger had less than 2 times slowdown on average. However, PM test had less bug coverage. For bug detection capability, PM debugger has the best bug detection capability. In addition, PM debugger detected 19 new bugs in memory cache and 2 new bugs in PMDK. Thanks.